Our recording.
Hey guys, this is the Nerd Herd here. We're going to go over chapters 4 and 3. And my name is Hope Windle.
I'm Kimberly Emerson.
Crowe at your service.
Katie Hardister.
And I'm Danielle Gillham. All right, Kimberly, what is divisibility?
Divisibility is to be able to be divided evenly with no remainder left over. So we do that by setting rules for numbers. So we know if it's divisible by 2, that means the last digit of 2 has to be even. If it's divisible by 5, the last digits have to be 5 or 0. If it's divisible by 10, it would definitely have to just be 0. Okay, Chris, does every number have a divisibility rule?
That's a pretty good question, and the answer would have to be yes. Every number has some kind of divisibility rule. 2 has a divisibility rule, 5 has a divisibility rule, 10 has a divisibility rule, 360 has a divisibility rule. Every number has some kind of rule that you can follow in order to figure out whether it divides evenly or
not. Okay, so we're going to do number 2. So let's remember our rule for 2. The last digit has to end with an even number. So let's look at the first one. We see 684. 4 is an even number, so that's a yes. The next one is also, last digit is a 4. The next one is a 1, so that's odd, so it's a no. 0 is an even number. The last digit is again 0. And the next digit is 8, and that's even as well. So let's look at the rules of 3s. Danielle, can you give us some examples?
Yes. On the divisibility rules of 3, you're going to add all the digits of the given number, and then if that number you get, the sum, is divisible by 3, then the number is originally divisible by 3. So all but 2,676,740 was divisible by 3 because its sum of all the digits had a remainder. So that's why it didn't. What about divisor 4?
So with divisor 4, we can take a look and see. Just getting my pen out here. So we can see that the rule is that the last 2 digits are divisible by 4. So the last 2 digits, so in this case 84. 84 would be divisible by 4, so we'll put a yes here. But 64 would not be divisible by 4. So we'll put no. So each time, just remember that we're looking at these last 2 digits here. And that's how you would solve this here. So 51 would be no. 90 would be no. 40 would be, of course, yes. And then 28 would not be. And that is how we would go through that.
Okay, so let's look at 5. So let's remember the rules for that. So it's pretty simple. So the last digits would have to be a 5 or a 0. So we see 684, that's a no. 4 again, that's a no. 1, not 5 or 0, so that's a no. 0, definitely yes. The next one is also a 0. And then the last one is 8, so that's a no. So let's look at the number 6. Danielle, can you give us some examples of those, please?
Yes, so if the number is divisible by 2 and 3 in those rules, then the number is also divisible by 6. So there's 2 numbers that weren't because one of them wasn't divisible by 2, and then one of them wasn't divisible by 3. And the rest were divisible by 2 and 3, so the numbers were divisible by 6.
Awesome.
So I have a question with that, Danielle.
Yeah.
So if they're not both divisible by the number, then that means the entire number is not, right?
Correct. So
okay.
If one of them is, but one of them isn't, then it's still not going to work because it has to be 2 and 3.
Okay, I understand.
Thank you. How do you tell if a number is divisible by 7, Chris?
Well, Danielle, the divisibility for 7 rule is probably the more complicated ones that we've run across so far. So using 51,051 as our example, The rule begins by taking the final digit of the number, so in this case 1, we then double that number, so we get 2 in the long run, and then we take that 2 and we'll subtract it from our newly created numbers, so 5,105, which gives us our new number of 5,103. And then we will take that new sum total and divide that by 7. And if it turns out as an even number, then the whole original number is divisible by 7. And if you want to subvert the whole having to subtract to find a bigger number, you can simply break down the sum total number further and continually find numbers that are divisible by 7 until you reach the end of the line, which will typically end up being 0. But in number about 7, why don't we find out the divisibility rule for 8, which I find to be a much more interesting number.
Sure. So 8 is not as tricky as 7. So we have to know if the last 3 digits are divisible by 7. So again, we're just going to be looking at here. Let's see. We're going to be looking at, so this one is only 3 digits long. So is 684 divisible by 7? The answer would be no. But this one here, so we're going to include 0 just to keep us, not confused here. So 64 would be divisible by 7.
You mean 8 or?
I'm sorry?
Do you mean divisible by 8?
I do.
Oh.
I think. Let me check. Do y'all remember if it's 8 or not? 8 or 7?
I think it
I
would be.
believe 8.
I think it would be 8. And also, I have another question.
Yeah.
Could we also use the same kind of pattern that Danielle used? Like, could we break down the factors of 8? Like, would it have to be divisible by both 2 and 4?
We could do that. Yeah, so I'm sorry, so changing that to 8. So would 051 be divisible by 8?
I don't think so.
No. And what about 490?
No.
I don't think so.
No. And 740?
No.
No. What about 528? It ends in an 8. Would it
Yes.
be?
That would give us a whole number 66. So we're good.
All right. Well, thanks for checking me up, guys.
That's what we're a team.
Absolutely. All right. So what about the rule of 9s?
So on the rule of 9s, you add up all the digits of the number given. If the digits added together are divisible by 3, then the number is divisible by 9. Or if it's divisible by 9, it's divisible by 9. So there were 3 that were and 3 that weren't. Because 3 of the numbers had a remainder on the sum of the numbers. So that made them not divisible by 9.
Let's
Hey
look
Kimberly,
at 10.
how can you tell if it's divisible by 10?
It's simply just if the last digit has a 0, because anything with a 0 on the end can be divided by 10. So 684 now, 4 now, 1 now, 0, yes, yes, and then no. And we can tell by the last digits. So let's look at a trickier one. How can I tell if a number is divisible by 11? Can you help us out?
This one is going to be really tricky. So I'm probably only going to show us one example with the more complicated one. You're going to take the first digit and you're going to add it, and then you're going to subtract the next digit, and you're just alternating those. So what I mean by this, let me go ahead and find my pen. Wait, I forgot. Let me take this here, and we're going to break down this number. Oh no, I can't see my numbers. There we go. We're going to start with, we're going to say plus 2 minus 6 plus 7 minus 6 plus 7 minus 4 plus 0. Go ahead and add our numbers. So plus 7 is 9, plus 7 is 16 plus 0. So we're going to say 1 plus 6 is 7. And then we're going to take negative 6. Wait, that's not right. Let's keep 16. And then we're going to say negative 12, and negative 4, which would be give us negative 16. That's going to equal, and 0 is divisible by 11. So following that pattern, you can find each of these numbers to see if any of these are going to be divisible by. But let's go ahead and do one more just to see if we can get this. So we're going to do plus 6 minus 8 plus 4, and that's going to give us 10 minus 2, and 2 is not divisible by 11. So that's pretty much how that rule goes. So whenever we're talking about divisibility, we've got all kinds of rules and all kinds of fun little things we can do. I'm going to go ahead and clear this off so we can keep on going. And
That one was pretty
now,
simple.
cool stuff about divisibility, we can see our chart here. And we're just going to fill in all these cool little things so we can know what is and what is not divisible by our numbers here. And I think that's a pretty cool looking chart that kind of shows us, you know, and like we said earlier, you can see the patterns. Like whenever you have your factors that are factors of 6, like 2 and 3, it also is divisible by 6. And the same thing goes with 8. And then we get another cool thing is if something isn't divisible by 2, which is an even number, then it's not going to be divisible by any other even number because 2 is a factor of those even numbers. So that's pretty cool. So now that we've done divisibility, Kimberly, can you introduce us to the process of nines or casting out nines?
So the process of 9 is to cast out 9. So we'll cast out the number 9 and anything that adds up to equal 9. So we see that we have 616 plus 7,496 96,244 equals 112,790. So this is kind of like for a check. We'll check our answers this way by casting out 9. So we'll do 416. So as we can see in 416, we don't have anything that adds up to equal 9 or the number 9. So 4 plus 1 plus 8 is 11, and we don't want to keep that double digit, so we'll add 1 plus 1 equals 2.
I'm sorry, somebody has some background noise that's like really interfering with their microphone. Anyway, keep going, Kimberly. I'm sorry.
And then we have 7,490, and then we don't, we see we have a 9 there, so we'll cast that out, which leaves us with 7 plus 4 plus 0 equals 11 again. Again, we're going to do 1 plus 1 equals 2. And then we have 96,844. Again, we're going to cast out that 9, which leaves us with 6 plus 8 plus 4 plus 4 equals 22. Again, no double digits, so we're going to do 2 plus 2 equals 4. And then we're going to keep up with this side. So we'll do 2 plus 2 plus 4, which equals 8. And now we're going to do the opposite side of the equal sign to see if it matches. So we have 112,790. So when I look at this, I can see 2 plus 7 will equal 9, so we'll mark off 2 and 7, and then 9 and 7, which leaves us with 1 plus 0 equals 2. And as you can see, 8 and 2 do not match. So that did not work for this problem.
That's one long-winded process there.
It is. So let's look at something different. Is counting out 9 foolproof? Chris, can you answer that for us, please?
I can. The method of counting out nines is, for the most part, a largely accurate method of seeing whether a number matches, the remainders match. And one way I'm going to show you that is to, first, we're going to have all the numbers added together. Now, the given answer could be right, but it could also not be right. So what we're going to do is we're going to add them all together first. And you see we get the answer 23,992. Now, using addition, we find out that's the 100% accurate answer, but are we 100% sure about that? And the way we can find out is we take that sum total number and then we divide it by 9, hence the counting out 9's part. And whatever number we get, the remainder is what we want to pay attention to. So in this case, we have a remainder of 7. So now that we have the remainder for the simple addition part, what we're then going to do is we're going to take every single one of the original addition numbers, we're going to bring them over, and then we'll divide all of them by 9. And once we have their remainder numbers, we then add them all together to get our next sum total, which in this case is going to be 16. And then what else will we do but divide that sum total number by 9? And if remainder matches 7, then we know that 23,992 is the accurate answer, and therefore it will match, as opposed to the given answer of 209,940. And as we can see, the remainder is 7 when 16 is divided by 9. So we can tell that 23,992 is our correct answer. And the other one is not. It is a liar. So, Danielle, can you tell us, is there a simple way to do a subtraction method on the process of 9s?
Yes, there is. So I found out there was a simple way by just adding instead of doing the subtracting. Just reverse it. And so instead of doing the 78,000 minus, I made it into an addition problem. And then we're going to add up all the digits. And so for the first row, I got 32. And the second row, I got 11. And I crossed out the 3 and the 6 because if you have 9s, then you can, eliminate the 9s. And I did that on the bottom row as well. And so we got 32, 11, and 8. And then you're going to break it down into 1. So 3 plus 2 is 5, and then 1 plus 1 is 2. And then you're going to add these up together, and you're going to get 7. And then the total for the bottom number was the 8. So the 8 and 7 doesn't match up. So therefore the answer must be wrong. Like Chris said though, these don't always work out, but if 8 and 7 wasn't correct, then it's obviously not correct. So the actual answer here is 78,362 minus 3,674 was not 74,678, it was 74,688. It was off by 10. Can we still cast out 9s in multiplication?
We can. So if we take a look here at this equation, let me get my pen out. Pink's good, right guys? So if we take a look here at this equation, what we're going to do is start by just writing 3 plus 3 plus 7. So we're just taking this number here, and that equals 13. From there, we're going to add 1 plus 3, and of course 1 plus 3 is, what is that guys? 4. That's right. Great job. So from there, we're going to remember 4. So then if I add 6 plus 2, Kim, do you think that I should write plus 0?
There's no point.
There's no point. I didn't think so either. So 6 plus 2 is 8. So then we can say 8 plus 4 equals 12. But I don't want a double digit number. I want a single digit. So what I can do is equals 1 plus 2 equals 3. So now I've used both of these numbers here. So I took 8 and 4 and I added them together, of course, got 12. 1 plus 2 is 3. So now I can take here, and Kim told us that we don't have to write these zeros, so we can just go ahead and cross them out. And again, we don't have to write 9s, right, because we're casting them out. So let's just do 2 plus 4.
Does somebody have a TV on or something? Like I can barely hear someone talking because there's like background noise. Somebody has background noise. I'm so sorry.
No, that's okay. I don't have a TV on.
I don't either.
So
No. Maybe we could just make sure our volume's turned down. But so we see that 6 and 3 do not match. So we would just write not a match. And that's how we would use this for multiplication. It's essentially the same steps, I believe.
it's
All
very well
right.
put together.
Yeah, I like that.
And I'll clear my annotations there. So, hey Hope, what does it mean if you have different remainders?
Okay, like we've all been talking before about all this, I'm actually going to reiterate with this problem here. And what it means whenever you have a different remainder is basically what we've been saying before, like your math is wrong. So the casting out nines is basically just a method that we're using to check our math. It's not necessarily like Chris was saying, it's not a foolproof method. So we're going to go through here and we're going to cast out our nines. We can see here that these are, so we have 8. And then we're going to have, this is a 9. And then we're going to have 7 plus 4 is 11. 11 minus 9 is 2. Or you could simply add the digits together. And then you can see here, we've got, what is this, 10, so that'd be 1. Hang on, let me do this. Let's do this. That would be 1 and 9. We have 14. So we have 5. So 8 minus 2 does not equal 5. It would equal 6. So this wouldn't work here. So we need to go back and check somewhere.
Mm-hmm.
So what we would have to go back and do, we would actually have to go back and just do the math problem. So whenever you have a remainder that's not the same as your total, you would just have to go back in and just recheck your math. So we would take this out, and we would have our 8 here, then we would have 15, this would be an 8, and we can already see that we made a mistake earlier.
Mm-hmm.
We just go, oops, and then we'd have 6. Sorry, my tool was kind of going wonky on me. So we would see that we actually made a mistake right here. Right over here, we've made a mistake.
So we're just off by tens.
And check with our casting out nines. And that's, again, it's just a way to check math. It's not a way to do the math itself. So that is a really fun kind of thing. So now that we've learned about casting out nines, we're going to learn about how to use measuring rods. And Kimberly, can you tell me what these rods represent?
Okay, so the rods represent 1 centimeter squared each. So you'll add 1 centimeter for each individual square that makes up the rod. So let's look at a problem, and I can explain that a little bit. So which rods measure up to the 9 rod? So we see that 1 and 8 measure up because 8 plus 1 is 9. 2 and 7 make 9. 3 and 6 make 9, and 2 and 5 make 9. So as we can see, they are all 1 centimeter each square.
Cool.
So Danielle, can you tell us what makes up the 6th rod?
Yes. So it's basically like doing factors. Your factors of 6 are 1 and 6. So we took 6 1 cubed. And then you have 2 and 3. So I did 2 of the 3 blocks and 3 of the 2 blocks, and then 1 of the 6. Can a train have more than 2 blocks, Chris?
That is a good question. And first I need to explain what a train is. So a train is, in simple terms, it is combining 2 or more different rods together to create one larger rod, a train of sorts. And as for a train having more than 2 blocks, it's actually necessary. A train has to have at least 2 blocks in order to actually be a train rather than just one rod individually. And the number can continue to increase because that is the nature of the train.
Okay.
Now, Hope, how can we use these bars to find the greatest common factor of these numbers?
Okay, cool, Chris. So, like earlier, we were talking whenever Kimberly and Danielle were telling us about the 9 bar and the 6 bar. We're going to go ahead and see all the different things that can combine into the sixes. We know ones can fit in both 6 and 9, but two cannot fit in both 6 and 9. But we can see my animations are going kind of crazy, but we can see that a 3 can fit in both, so we can deduce that 3 is going to be the greatest common factor in both the numbers 9 and 6. And earlier you were talking about trains and stuff, Chris. So, um, Katie, can we add trains together, or can we add blocks together?
We sure can. So if you click through, then we can see if we have an 8 and a 10 and we add those together, then we can actually just make an 18 train.
Very neat.
So, Hope, but what is a least common multiple?
Oh, so kind of like a greatest common factor, you're going to see the greatest number that can break down into. A least common multiple is going to be the number that is whenever you multiply the numbers out. So, like for example, for 9 and 6, the greatest or the least common multiple would actually be 18, like that number train that you were showing us earlier,
Okay.
because it's going to be the closest number that both numbers can multiply to get. So I'm going to show you guys an example of least common multiple, and it looks like I forgot to do my animations correctly. But so we're going to go through here, and we're going to see that first we're going to start off with the smallest prime number. We're going to divide it by 2 because we see that we have an even number. And that's going to give us 24. And then we're just going to drop these other numbers down because we haven't done anything with those yet. But 24 can be broken down even further, and it can be to 12. And we're going to continue breaking these numbers down until we get to this. We're going to bring it all the way down to this prime number. And then we're going to take those prime numbers and we're going to put them all together in an easier way where we can read them easy. And we're going to see that we have 2 to the power of 4, 1 3, and 2 5s, which gives us 5 to the power of 2, and 1 13. And then we're going to multiply all those together, because if everything matched up together, then we could remove it. But since each number is unique, we're going to have to use all of those numbers together. And crazily enough, the least common multiple between the numbers 48, 25, and 65 is going to be 15,600. So a lot of our numbers aren't going to be quite that high, but unfortunately, the examples we have today are. And I was talking a lot about prime numbers and stuff. Kimberly, can you tell us what exactly prime numbers are?
I sure can. So prime numbers are whole numbers that are greater than 1 with the factors of only 1 and the number itself. So here's a couple examples that I put together. Not all of them, but a couple examples are 2, 3, 5, 7, 11, 13, 17, and 19. All of those can be divided by 1 and the number itself and nothing. So you were talking about least common multiple. So we're going to use our LCM to fill out this chart to find our prime numbers. To find the least common multiple between these numbers 40, 12, 44, and 336. So as you can see, 40 can be divided by 2. So we can divide those and get 26, 22, and 36 will stay the same. We can divide that by 2 again. Get 10 and 3, 11, and 336 still cannot be divided. So we'll divide by 2 again. And we'll get 5, 3, 11, and 336. And then when I look at this, we can divide by 3 and get 5, 1, 11, and 121. And then we're going to divide by 11 and get 5, 1, 1, and 11. So that gives us all of our prime numbers. And we're going to keep all those prime numbers. And we're going to multiply them all together. As you can see, we can do it the long way and do 2 times 2 times 3 times 3 times 5 times 11 times 11. Or we can put it in power form and make it easier on us. And after we multiply all of those, we'll get 14,520 as our least common multiple. That was a lot of work. So what exactly are prime numbers, Katie?
Well, I know that you kind of talked about prime numbers, but just kind of reiterating what you said. So, a prime number is a positive integer, and I know that you told us before that an integer is just kind of a fancier way of saying number. So, a positive number, if you will, with only two factors, itself and 1. So, going over those, I went through and I know that you only did to maybe 19, so here's just the rest of them through 100. We could also talk about what composite numbers are. And I didn't include this in my slide, but because you've already talked about prime numbers, I just want to give our peers a little bit something else to talk about, or to think about rather. So a composite number is a positive integer or number with more than two factors. So if we went through and we listed all of the other numbers, so through 100, then we would see that, like 4, for instance, it's not included between 3 and 5. That would be what's called a composite number instead of a prime number. And we could go through and talk about each of those numbers, but we won't go through that today. So, hey Chris, does this work when finding the least common multiple for both small and large numbers?
As a matter of fact, yes, this method is accurate for both small and large numbers.
Okay.
And while my squares don't appear to be there at the moment, going through the graph, we can see that, now they're appearing. Going through the whole graph, now technology is terrible. Going through the graph, we can see that the largest number is actually the first one instead of being left last like some of the other previous graphs.
I see.
So breaking down every single number, we can see that 2 and 5 are the most prominent and frequent numbers on this list.
Mm-hmm.
They are the ones that are bringing down most of these numbers into their prime forms, and once they're brought down, they'll be put into their prime factorization forms, and then obviously multiplied into their least common multiple. Similar to the processes, for example, of the greatest common divisor.
Okay.
So yes, it does work for both the large and the small numbers. It's just a somewhat arduous process.
Sure.
So, Katie, I need you to answer me, what is the LCM? What is the least common multiple?
Sure. So whenever we're looking at the numbers that we were just looking at, so between these two, the least common multiple, do we see two numbers in there that might work? If we go ahead and click to the next slide, Miss Hope, or to the next, no, you're fine. So we see here that the least common multiple of each of these is, we see here 48 here and 84. So 48 and 84 equals 336. So using that, now that we know that 48 and 84 are our least common multiples, we're going to use that with this equation here. Hey Kim, what are the teeth in this gear that we're looking at?
And that was my biggest question, is I barely knew what a gear was, so the teeth on it, I have to do some research easily enough. It's just the little rectangular pieces that come off of the gear. So, and they transmit motion, so that's what keeps it going.
Mm.
So let's look at this example. So we see that point A has 48 teeth. We see that 84 has, B has 84 teeth. So let's look and see how many rounds will it take A, the one that has 48 teeth, to meet 84 again, point B. And we're going to use the LCM, which you just told us what that was, 336, and we're going to divide that by 48 since we're looking for point A. And we're going to get 7 rounds. It's going to go around 7 times to meet 84. So let's look at B. So we're going to do the same exact thing. Since we know B has 84 teeth, we're going to divide the least common multiple, 336, by 84, and that's going to give us 4 rounds. And the reason why that number is much smaller is because that is much bigger.
Mm.
So what if I mess up the prime factorizations for the gears? Chris, can you please tell me the answer to that?
I can. And messing up in a prime factorization is a very easy mistake to make. and hopefully one that you'll quickly learn from. So the most effective method is probably the one you see on screen, which is a prime factorization tree, which is basically just placing the given number and then using the branches to slowly break down that large number into its prime numbers. So, for example, you see 42 on screen. Now, breaking down, you get 6 and 7. 7 being a prime number, we leave it alone. 6 can be broken down further to give 2 and 3. And since all of those are prime numbers, the prime factorization for 42 would be 2 times 3 times 7. Now, if you mess up, such as getting a wrong number that doesn't equal your original prime factorization number, then you might have multiplied wrong, or you might have broken down wrong, or you might have placed a prime number where you should have put a number that can be broken down. An easy mistake to fix as well as spot. So it's just a matter of going through and using your critical thinking and deductive reasoning skills. You just loop back around and check your work. Simple as that. So we see here we have the gears. We have the larger one having 84 teeth, the smaller one having 48 teeth. So for the savior of our time as well as the workload, I've simply brought down the numbers 48 and 84 into their prime factorization forms. 48 being 2 to the 4th times 3, and 84 being 2 to the 2nd times 3 times 7. And just as a quick side note, if you're curious what the 4 and the 2 above the 2's represent, those are known as exponents, and they represent exponent form. So when you see 2 to the 4th, it's actually saying 2 times 2 times 2 times 2 times 3. And so what you want to do next, once you've gotten both your prime factorization forms, is you want to combine them. And so as you see there, we have 2 to the 4th times 3 times 7. Since the 3 is the same in both forms and 7 is non-existent in the 48, the larger exponent form, 2 to the 4th, will simply swallow 2 to the 2nd, and then they'll combine into what you see there. And then you will write out the equation as a whole, multiplying it to get the number 336. And once you've gotten that number, you simply divide it by the amount of teeth in the smaller gear, 48, and you'll get your answer 7. So these gears will have to make 7 rotations before the same teeth that are currently touching will touch again. It's an arduous process, but a well put together one.
All right, so if you look at the gears and you break it down, we've been using the factors and prime factorization little trees. So 84 and 48, they were both divisible by 12, and then that broke it down to as far as it could be. So 84 divided by 12 was 7, and 48 divided by 12 was 4. So instead of looking at a big ratio of 84 to 48 on the teeth gears, I broke it down to 7 to 4. So your bigger gear is simply going to go around 4 times, compared to your smaller one is going to go around 7 times when they work together.
So basically what you're saying is every time the smaller gear is around 7 times, the bigger gear will have to go around 4 times to come to the same place.
Yes.
Ratio, that's pretty cool.
Can we use the casting out nines method when finding amount of gear rotations?
Actually, yes, and I am so glad you guys asked that because I heard you guys talking about the prime factorizations earlier and how we know 48 teeth and 84 teeth and so on. Whoops. So I'm going to write on here real quick. So earlier, Chris was telling us, where's my tool? Come on, tool. Here we go. Earlier, Chris was telling us that it was 2 to the 4 times 3 gives us 48, right? And then he said, what was it? 2 to the 2nd times 3 times 7 equals our 84. Was that correct?
Yes,
okay,
it was.
He brought us down here, and we found the least common multiple was going to be 336, which was 2 times 4 3, 7. And then we were saying, oh, we're going to divide that. We're going to add all this together and divide by 3. But hold on a second. This right here is 48. So we can just cast that completely out, and it gives us this answer 7 right here. And if we were going to do the same thing, breaking it backwards down to 84, then we could just say, we cast out all these things here, and it would just leave us with 4. So no matter which way you're going to do this math, you can just, like we did earlier with casting out 9s, you don't have to go all the way to 336. If you were doing the factorization first, you figured out to find it, you can say, hold on, I found 48, so let me just cast that completely out, and it would save yourself a little bit of time. So we found out that make 7 a point and point B to be back to each other. Now let's do something a little bit more fun. We are going to find the magic number. So Chris, could you tell us how to find a magic number for our square?
I can, Hope, actually. So looking at the magic square we have here, we have our two given answers, 0 and 1. So the magic sum is the sum number that all of the numbers when placed in the chart are going to equal whenever they are added together. So that's all the way across, that's diagonally, that's vertically. Every which way it will equal the magic sum number. And to find the magic sum number, we're going to use x to represent that. We have to add all of our given numbers together. So we have -7, -6, -5, -4, -3, -2, -1, 0, and 1. We add them all together, we get -27. And then we're going to use 3 times x, the magic sum number, equals -27. So from there, it's simple division. What times 3 is going to equal -27? Well, that's going to be -9. So -9 is our magic sum number. So every which way that they go, they have to equal -9, which is going to help us when we want to place our numbers.
Okay.
Hope, what is the most logical step to take when you're first filling out the magic square?
Okay, well, what I did whenever I was filling out this square, after finding the magic sum, I was like, okay, so I see I have 0 and 1 to start out with. So, whoops, what have I done here? I'm trying to find my tool. Where do we go? Uh-oh. Let me move us back over here. Okay, I'm not sure where I went. So what I did was I
think you stopped screen sharing.
I did stop?
I believe so.
Uh-oh. Uh-oh. Let me go back to the screen share. I'm so sorry, guys.
That's okay. You have to share your work, Hope.
I know. I hit the wrong little thing. Here we go.
That's okay.
Let's do, it is hard. Okay, annotate. Hey, it's a good thing that happened because now I can fix my stuff here. So let's get back here to where did I go? Guys, I'm really struggling over here
You're fine.
with my technology. Okay. Okay, so let's just have our, here we go. Okay. Oh, there's my square. Now I just need my annotate. All right. So I saw that I have 0 and 0 and 1. Balance this out. So I'm going to add my -7 here. If this is -7, then I need this to be -2. And if -7 and 1 gives me -6, I'm going to go ahead and add a -3 here. And then I have -2, -3, and this would be -4 because this is all total -9. And then this is going to have to be a -6. And look at there, that's also -9. So this is working out here for me. -2, -6, and a -1. And that'll leave me left over with a -5. And that was just a little fun way that I used to figure it out. I just tried to balance out my 0 and my 1. But I've heard our friend Danielle has a cool way. But Katie, how would you set up a magic box?
Well, Chris actually kind of answered this and he didn't even know it. He's smarter than he knows. So whenever we took a look here, let me get my annotate tool out. Whenever we take a look here at, Chris, what was those numbers? If we add all of these numbers together, you said negative 27, correct?
That is correct.
Okay, and then so if we take negative 27 and exactly what Chris said, x, let's place x there, and we know that our magic number is 9. So we could add a 3 here to say this x equals 3. So I could do a box that is 3 by 3, and that's how we would decipher how we would actually set up our grid for the box.
Just in case we need to draw it out for us.
Absolutely. And let me clear those so Miss Danielle can write on hers. You don't need my scribbles, do you, Danielle?
All right. So, Hope, you explained it very well, and you actually figured out the problem really fast. I unfortunately wanted to find a structured way, but I can definitely tell you're a puzzle person.
Yeah.
So this is the given magic square that we were given. And however, there is a little trick to figure out a magic square that I had found. And you kind of just flip it. So when you do this with the structure form, you're going to start with either, if you put all your numbers in chronological order, either your highest number or your smallest number in the bottom middle box. And then you go and you work your way up the list. So you're going to do it from mainly going down 1, which, okay, you're going to go down 1, and then since this is the end of it, you'll just go back up here, and then you're going to go right 1. So you keep doing that, and as you can see, you went down 1 to this. Where'd it go?
Yeah.
Down 1 and then right 1 right here. And you keep working your way, but if you go down 1 and right 1 right here to the 1, you can't do it because it's already filled in. So if you run into that problem and you notice that the space is occupied, then you just go up 1 and work your way from there. It probably sounds a little complicated, but it was super simple. And then when I added it up, all of them were negative 9. So, and then if you wanted to
It's a
have
very
it back in the
inventive
form,
method, you know?
thanks. So if you wanted to move it back, you'll just rotate it back.
I'm curious. Is this your own method, or did you find this somewhere? Because that's very impressive.
No, I definitely looked it up and found it.
Oh, okay.
And then tried it out with this problem,
hey, it's
and
still
then kind of just like
impressive, though.
rotated it around, and it worked.
Yeah, that's a really cool method.
It's strange.
Yeah.
Well, whether you're creative like Danielle or you're just a plug and chug like me just to figure out what's negative 9, whether you go horizontally, vertically, or, just
Diagonally.
no matter how you do it, if it equals negative 9, you did it correctly.
Yeah.
So I think that's all for us today, guys.
All right, guys. Thank you so much from the Nerd Herd. We hope you had as much fun as we did. Have a good night, guys.
Bye.
Good night.